So good afternoon, ladies and gentlemen. Welcome back to the second day of the interACT virtual final event. We are very excited to be presenting further results of our project today. And for those who have not joined us yesterday, a very warm welcome to the second day. So with me is my co-moderator, Natasha Merritt. She is professor at ITS Leeds. I'm Anne Schieben. I'm with DLR, that's the German Aerospace Center, and I'm leading a team of human factors researchers at the Institute of Transportation Systems. So let us have a look what we expect today. First of all, we have a summary or a sum up of the day yesterday. So I will speak briefly about what we did or what we learned yesterday, what we presented. And then it's our real pleasure to have Tom Alcom from the European Commission with us today. He will give a keynote, so you will hear a bit more what the Commission view on automated vehicles is later after my talk. Yesterday, we learned about the basis for interACT. Today, we are talking about the implementation and evaluation of the interACT research results. So it's about developing the human-machine interaction, implementing the demonstrator vehicle, and evaluating the interACT solutions. And after the talks, you have the possibility to ask questions. We learned yesterday that there was some confusion because we used Slido as well. So the question needs to be typed in this tool. It's the webinar tool where you can just put in your questions and we are trying to answer them. It could happen because we are more than 100 registered participants for today that not all questions could be answered. Our idea is that we collect the questions and that we put answers to your questions and upload them on the website just in case we can't answer all today. So please feel free to ask the presenters questions after the talk. I will now give you a brief summary of what we did yesterday. For those who haven't joined us yesterday, just a quick overview on the project itself. It's funded by the European Commission under the Art 04 call and had a runtime of 36 months. We had to extend our project duration due to the COVID outbreak, so it runs now till September 2020. We received a funding of 5.5 million euros from the Commission, and I was acting as the coordinator. As you can see on the map, we had a nice balance of 8 industrial and academic partners from 4 European countries, Germany, Italy, Greece, and the UK. And here you see University of Leeds as partner, CRF as partner, Hella, Bosch, BMW, and the German Aerospace Center as coordinator. And from the academic perspective, the Technical University of Munich and ICCS from Greece. It was our pleasure to be selected as twinning project for an US European twinning activity with AV in 10. This was our twinning project, and it was nice to have the exchange there. So let me go one step further. What did we do in the project? You have seen that yesterday already. First of all, we tried to understand what human-human interaction is like at the moment. This was the talk given by André Dittrich yesterday. And then we were trying to find solutions on how automated vehicles should act in mixed traffic environments, not only with other traffic participants, but also with the onboard user, because the traditional way of interaction is somehow broken by the AV, because the AV brings its own intelligence and needs to make decisions on how to interact in such situations. So this is a slide that we use quite often during our presentations. It just shows the different objectives that we had in the project. Yesterday, we learned more about the basis, as I said, so the psychological models of how humans interact with each other in mixed traffic environments, as well as the modeling of those aspects. Then we had the intention recognition and behavioral prediction as topics of yesterday, and the development of the communication and cooperation planning unit, it's CCPU, and the safety layer to make the interaction of the automated vehicle really safe. We did a Slido poll yesterday, so to learn more what was most interesting for you. And as you can see here, yesterday, many of you pointed out that the observability, the interaction models, so what is going on in real traffic and how do we use that for the design of automated vehicles is of most interest for them. Thanks for doing the poll yesterday. I will now show you what we have planned for today. As I said, it's about the implementation of what we are doing or what our solutions were in the project. So first of all, after the keynote from Tom Alkins, you will hear more about the development of novel onboard and external HMI elements. Then we will go into the build-up of the demonstrator vehicles. It's a pity that we can't show it in Munich due to the COVID outbreak. That was our original plan, but Fabio Tango from CRF will do his best to explain you what we did for the demonstrator vehicles. So we had build up 2 demonstrator vehicles, one from BMW and one from CRF that you see on top. And last but not least, very interesting for all of us are the evaluation results. So this is the 5th objective, that we try to find out what kind of methodology do we need to use or do we need to apply when we would like to know more about the interaction behavior and assess the quality of interaction design that we did for the automated vehicles. So this is what Jim Mund from ITS Leads will present today, as well as the evaluation results from virtual reality studies, simulator studies, and test track and real life studies with those 2 demonstrators. So this is more or less what you expect for today. Natasha, we have thought that Slido worked well yesterday, so we would like to ask you some Slido questions again. And Natasha, maybe you can just share your screen to explain the audience how this will work today.
Yes, sure.
Thank you.
Okay, so just in case you're not familiar, you can see my screen hopefully now. Slido.com, you can either use your phone or your computer and use that hashtag number there. And please vote in your opinion how important an additional external HMI component is. And we have nearly 100 people registered, so we'll wait and see how that comes along.
Okay, that's a nice mix. Natasha, I can't see you on the video. Did you switch it on?
No, I haven't switched it on right now, just to make it easier, if that's okay.
All right, okay. So it's just me, all right.
Yeah. Letting people focus on the voting. Oh my goodness, it's very mixed.
It's really mixed.
Yeah.
How many votes do we have now? Okay. Okay, then I hope that you will learn a lot today because, as I said, we will present the evaluation results as well in the last talk of today. What's the next question, Natasha?
So we have, do you expect any positive impact from external HMI? So that's back on the screen now, hopefully.
Oh, that's interesting.
I personally thought the 2 questions were relatively similar, but yes, we're getting slightly different view now. See if we can get it back up to the sort of 80 people we had before.
Okay.
Okay. So yeah, that's the end of my Slido
That's interesting.
questions for
Okay.
now.
All right. So I hope that you will enjoy all the talks that we have prepared for today, because they are giving some answers to the questions that we asked in the beginning. I would like to introduce now our keynote speaker, Tom Alcombs from the European Commission, and would like to ask you, Tom, to get prepared. Thank you for joining us for today. You know that we originally planned to have the meeting in Munich on 1st of April, and Tom was announced as keynote speaker as well for this event. Thanks a lot for being with us. Tom is a policy officer of connected and automated driving at the European Commission, Directorate General Research and Innovation, and he brings more than 20 years of experience in the field of ITS, CITS, and automated driving, and was a constant factor for the Dutch Ministry of Infrastructure and Water Management. Tom Alcombs is now working with the European Commission on advancing connected and automated driving in a responsible manner to deliver societal benefits. In his capacity, he was co-organizer of the second European Conference on Connected and Automated Driving, and he is the co-chair of the working group on cooperation and coordination of R&I in the European Connected, Cooperative and Automated Mobility. So welcome, Tom. We are really looking forward to hear your presentation on the view of the European Commission. Thank you for being here.
And can I remind everybody, I'm sorry to interrupt, Tom, just in case people attended a little bit later, if you have any questions, you can use your GoToWebinar to ask the questions. Slido is not open for questions. Sorry, Tom, please do go ahead.
Thank you, Natasha.
Okay, no problem.
Thanks.
Well, thank you. First of all, thank you for inviting me. It's a pleasure to be here. Thank you also for the introduction. We really think that this is an important topic, and we would like to provide you the EU perspective on connected, cooperative, and automated mobility. So I have prepared a couple of slides that I would like to present to you. In the current framework, Horizon 2020, we had several calls on automated road transport. And you can see here that there was a large variety of elements where we focused on. It's not only technology anymore. And I think that for this project, for interACT, you can see, well, the safety and end user acceptance is quite important, and also the human-centered design of automated vehicles. We had roughly 350 million euro available in this framework, which will come to an end this year. And this is an overview of several of the projects, and you can see there that interACT is also mentioned. Let's go to the next one. Yeah, so I made a selection of several other European projects that are related to human-centered design and also consumer trust and acceptance of automated vehicles, in which interACT is, of course, one of them. And I put them in alphabetical order. So you see that there are quite some projects focusing on the human-centered design and, let's say, the non-technological component of automated driving. I trust, by the way, that all the slides will be made available to the participants afterwards. So you can also read some of the information afterwards, and I've provided the link here where you can find more information. One of the latest projects in this framework that focuses on the human-centered design for the new driver role in highly automated vehicles is called Hadrian, and it recently started, so there are not a lot of results available yet. However, there is a website available. You can go there to check what their focus is on. On the right side of the slide, you can see the partners in the consortium. And what I like is that this project also truly looks at the interaction between the traditional components of vehicles, infrastructure, environment, and the users, and takes a holistic approach there. And as with many of these European projects, of course, we also count on not starting from scratch, but also using all the lessons learned from the previous projects. And they have come up with a concept that is called fluid HMI, where there is constantly, let's say, some sort of monitoring going on to see whether the driver or the vehicle is better positioned to perform the task and to handle transitions. So now maybe flashback to a time where we could have physical meetings. I must say I really miss that, and hopefully we can soon see each other again face to face. But it's already a year and a half ago that we organized this European conference on connected and automated driving. And I wanted to remind you of some of the major issues that were discussed there, especially the ones on safety validation, but also ways to gain trust, the societal and user acceptance of connected and automated driving systems. Also, ethical issues were raised at this conference, and here I can mention to you that we have formed an expert group to give the European Commission recommendations on these ethical issues that are raised by connected and automated driving. This group is now finished with their work. We have their report, and it will be published soon. It is not available yet, but it's a matter of a couple of weeks. So if you're interested in that, keep an eye on our publications. Some of the conclusions of that conference, and I think most of you will recognize that, is that we kind of passed the hype of automated vehicles and that realism is settling in now. So we have a shift where we go from potential and promises really to practice and public involvement. And compared to the first conference that we had, we also see a major shift from the more technological topics towards the non-technology related topics. If I recall correct, your project started in May 2017. That also means that the preparations and the call text, that was all done around 2016, starting at that time. And that was really, let's say, the peak of inflated expectations for connected and automated driving. If we go to the Gartner hype cycles, I find them quite illustrative. I went back in time, and in 2010 it was the first time where we saw the topic of autonomous vehicles emerging there. Of course, on the traditional left side, with an expectation that it would take more than 10 years to reach the plateau of productivity. And for some reason, the year after, it disappeared from the cycle. I will not show you all 10 pictures. Then it re-emerged, and as you can see, in 2016, it was at the top or just over the top of inflated expectations. At that time, at conferences, there were a lot of very positive stories about all the magnificent characteristics and all the problems that could be solved with automated vehicles. But I think what you have seen also in the course of your project is that in the past 4 years, we have seen more realism, because if you shift from theory to practice, you also run into a lot of complications. And I would say driving in mixed traffic with automated vehicles is one of those really tricky complications. So this is one of the more recent Gartner hype cycles. I guess we will see another one in 1 or 2 months coming. But what they did cleverly is also make this distinction between some levels of automation. So clearly, level 5 automation is far, far away if we will ever reach it. That could also be a philosophical question, by the way, but let's not dwell on that right now. And for automated driving level 4, you see here that it has progressed quite a bit. Although I must say this term is of course not descriptive enough, because automated driving level 4, that could be a shuttle in a dedicated area, and we have those for almost 20 years and they are functioning. So in that sense, you could say it is already at the plateau of productivity. But then again, it could also mean a person vehicle trying to drive on the highway in level 4 capacity, and that is still quite far away. So far for the expectations. I also wanted to share a couple of words with you on the single EU-wide platform on CCAM for open road testing that we launched last year. And the idea here is that we also develop an EU agenda for testing, and that we improve the coordination of research and all these testing and pilot activities. And we do this with several stakeholders. We should also, for instance, agree on common evaluation methodologies, try to facilitate access and exchange of data from these tests so that we can also learn from each other's lessons. And this is also to assist the Commission in various thematic areas. As you know, I think that the tricky part with automation is that it only works if all elements are fulfilled. So you cannot do it if only 80% of the requirements are fulfilled. So in short, you need technology that works, you need a legal framework that allows it, you need adequate infrastructure where it fits, and you need, of course, humans that are willing and able to use it. Only if those 4 major components and all the subcomponents that are related to that, only if you fulfill all those, then you can have automated driving in such a way that you also reap the societal benefits of it. So that's why we launched this platform where we have several working groups. The working group 1 was working on the EU agenda for testing. This group is now wrapping up with the final meeting next week, no, in 2 weeks. And then this will shift into the partnership for the next framework, Horizon Europe. I will tell you a little bit more about that in a couple of minutes. Then the working group that I am chairing is working group 2 on the coordination and cooperation of R&I and testing activities. And in this working group, we work on a common European knowledge base, a common evaluation methodology, and we try to set up a framework for test data exchange and lessons learned. The other working groups look at elements such as the physical and digital road infrastructure, road safety in itself, connectivity and digital infrastructure, and also cybersecurity and access to in-vehicle data. Now, I mentioned this European partnership under Horizon Europe. As you know, this is the final year of the current framework, Horizon 2020, and January 1st, we move into the next framework for 7 years. And here we would like to establish European leadership in safe and sustainable road transport through automation. Although I must say that we do not see automation as a silver bullet for all our transportation problems, and you need to look at a smart way to integrate all forms of mobility in, let's say, in the mobility ecosystem. But as long as there is a demand and it is sensible to have vehicles drive either transporting goods or persons, they might as well be connected and automated, because it gives you added value over manually driven, if done right, of course. For this partnership, there is a vision with some expected impacts for society. So once again, if done right, we could reap these kind of societal benefits in the areas of safety, impact on the environment, also inclusiveness, and competitiveness for the European sector. Now, for this partnership, it is important that different sectors and stakeholders are involved. And you can see here the different ones that are currently involved. So industry, public authorities and road operators, the mobility and logistics services, representative bodies, regulatory bodies, and research. And they are all working together. Here is an overview of a little bit of the background when it started in early January, where we called for the preparation of such a proposal. And we are now in the, let's say, in the final stages. We had seen the proposal, and currently this partnership is also working on the Strategic Research and Innovation Agenda, the SRIA, which will be the basis for, let's say, the work program in the next framework. And in this context, there are several clusters, thematic clusters related to CCAM. And I have a slide here where you can see them all. At the heart, we put the large-scale demonstrations because we realized that, of course, you can study a lot in controlled environments, you can study a lot in theory, but in the end, it has to work in practice. And we really think that large-scale demonstrations remain very, very important for the advancement of connected and automated driving. And centered around these large-scale demonstrations that will certainly take place in the next framework, there are different themes on in-vehicle technologies, on validation, integrating the vehicle in the transport system, key enabling technologies that are not only related to, let's say, the in-vehicle, but of course also the social aspects and user acceptance, and research coordination. And on the right side, you can see some of the sub-themes. And I think you can see here that the human-centered design and the human centricity, that is also very important in the interACT program, is scattered in various clusters, meaning that this is a very important element, and that's why it comes back in different clusters. I see that I'm getting to the end of the time that was allowed for me. So there's one thing I wanted to share with you, and that is this, the operational design domain framework. This is it in theory. I came up with this picture about 2 years ago, trying to grapple me with the concept of the operational design domain. And you could see this as a graphic representation of where automated vehicles can perform as intended and not. And for this one, it could be a level 4 vehicle that starts from home, drives to the highway, goes into automated mode, and then when it's in the blue rectangle, it is performing in automated mode. It's within its operational design domain, which is by definition limited until level 5. And then at the end of the operational design domain, the driver takes over again and drives manually to its destination. Now, of course, this is very nice in theory, but we all know what happens in practice. And I have many videos of showing you what can go wrong, and you must have experienced that yourself as well with testing. There are many instances in practice where things don't go as planned and the limits of the operational design domain are reached. And these are often related to infrastructure elements, to mixed traffic and other traffic on the road, and to adverse weather conditions, for instance. And I think it is a joint task for all the stakeholders to try and solve this in such a way that we try to optimize the operational design domain. However, we cannot make all these gaps disappear. So we should also really focus on the transitions of control into and outside of the operational design domain. And I think if you look in relation to interACT, I think gaps that are related to dealing with other traffic, that's an important task. And another one is also the vehicle behavior when it is inside of the operational design domain. Because automated vehicles do behave quite differently from human-operated vehicles at the moment. At least that's how we envision this. And in the end, that should be a bit more harmonized. So I think we still have a long road ahead of us. I think you made some major steps in interACT, especially related to these mixed traffic challenges. And I would say that communication, whether it's implicit or explicit, really helps also in negotiating with other traffic and expanding the contextual awareness of automated vehicles. But I also think that for the coming years, we need much more research and developments in this phase. So with that, I have come to the end of my presentation, and I don't know if there is time for some questions at the moment. I think I should. You have taken back control. Good.
Thank you, Tom. That was really nice to hear the European vision. And as a researcher, we are, of course, happy to hear that there's more research to do, I would say. I think we have time for some questions. As we said, please use the tool of this webinar, not Slido, for your questions. Just type them in and Natasha will help me to select some of the questions for you.
So Anna, this is Matthias. Maybe I can first ask an oral question. So Tom, thanks for your nice talk. So you talked about interoperability. So one thing that is always difficult in a project is that people have to build up the vehicles, get the sensors running and everything. So it would be nice to have something like an Airbus, a research Airbus on the road for research institutions, so that we can share the software more easily, and it's easier to for the PhD students to get going. So is there some activity going on in this direction?
Yes, I would say that in the working group 2 from the CCAM platform, we are trying to collect all these also lessons learned. But in cluster 7 of the partnership, one of the other tasks is also, let's say, some guidelines for on-road testing in Europe. So we try to collect also the practical experiences from projects like L3 Pilot, for instance, or Ensemble, in organizing those tests, and also how to deal with national exemptions and stuff like that. So not only the technical elements and lessons learned, but also the more practical ones. And what we would like to do is collect all that information and make it available through the European knowledge base. So that could be, let's say, a one-stop shop for all this information to start. So new projects would ideally never have to start from scratch.
Okay. Thanks. This was Matthias Althoff from the Technical University of Munich. So he is panelist today, and this is why he could use his microphone. Yeah. Are there any other questions coming in at the moment, Natasha?
I don't
from
see
the
any
audience?
other questions at the moment, no.
Okay, last chance for questions to Tom at the moment. Please type in your question if you have any. Okay, but this seems not to be the case. You were very clear. Thank you. Okay, then we're perfectly in time. Thank you, Tom, again for being with us today. The next speaker is now from interACT. So we will hear a talk of 2 speakers, Florian Weber from BMW. He is a senior researcher in user experience and was responsible for building up the BMW demonstrator at DLR, sorry, not at DLR, in interACT. And he was also leading the task on interaction design strategies. With him is Mark Kalb from the Haller company. They were our experts in light development, and Mark itself, he himself has an expert in pre-development lighting, and he was responsible for the work package for leadership and will give us an overview on what we did in that work package. So hi, Mark and Florian, we can see you and we can see your presentation. The floor is yours, I would say.
Just need to unmute yourself, please, Mark.
Okay, now you can hear me?
Yes.
Okay, thank you, Natasha, and thank you, Anna, for the introduction. Warm welcome also from my side. Yeah, to this special final event. So we can't get in touch with this HMI components today. That's yeah, it's a pity, but we have to do or have to live with this situation like it is. Maybe we can do it anytime afterwards. Yeah, my project and work package partner Florian Weber and me, we will use the next 20 to 30 minutes to tell you quite a few things regarding this development and implementation of a novel HMI concept and the developing of interaction strategy of automated vehicles. First slide is already well known, especially for all the guys who joined yesterday. Yeah, in this presentation, we tackle mainly the fourth objective or the fourth enabler, dealing with novel HMI elements which are necessary to substitute the interaction between human road users and other human road users today. Yeah, this is a short agenda for today. So as already mentioned, we want to tell you something about these interaction strategies we have chosen for the AVs, and then something about interaction design. That means chosen technologies on the one hand and signal design on the other hand. And last but not least, we want to make a transition to the next presentation, to the next work package, dealing with demonstrator vehicles. So you get an impression how we worked in this project from technical point of view and how the integration of HMI components went ahead during the last 3 years. So now I hand over to my colleague Florian for the first time. So
Thank
Florian,
you so much,
please
Mark.
check if it works.
Yeah, I do hope so, that we can switch to the next slide. I'm trying to, yeah, okay, that works. Okay, so thank you for joining us today, for having a look at our design process and all the outcomes. If you have joined yesterday, you might already have seen the flowcharts that are on the screen right now in a similar way. We used them throughout the whole project to describe our interactions. On the one side, what happens today in traffic, and on the other side, the interaction we would like to design for future automated vehicles. So just a quick wrap up on the flow charts for the people that did not join yesterday. We can see different interaction partners and different interaction elements basically on these flow charts, and we have from left to right a timeline, basically not to the second exact, but a timeline in how the interaction actually evolves one point after each other. And we developed in the project, also derived from all the observational studies that occurred in the work package 2, the talk of Andre that you heard maybe yesterday. We developed 3 designs. One was called the intention signaling design, so referring mostly to the intention of the automated vehicle, and the perception signaling design, and a combined design. I will shortly present you the design on an abstract level for now, and then later on we will go more into detail how it actually looked like. So if we look at this flow chart, we actually have a scenario where the AV is approaching an intersection and wants to turn right, and once it turns right, there is a pedestrian already waiting at the curb and wants to cross. So basically we can see here, I don't know if you can see my mouse. Yeah, exactly, that the AV is driving and already took the decision to decelerate a little bit. And then at this very moment, it detects the pedestrian and takes the decision to yield to the pedestrian. So shortly after, the AV starts communicating, obviously, that it wants to turn right into the intersection, which is a communication that already occurs today in manually driven traffic. And then it will also communicate that it will give way to this traffic participant on the outside. And then also the onboard driver that we see here below will also perceive this message. So once the pedestrian has passed, the AV starts to communicate that it will shortly start moving, and then it actually starts accelerating again, and the scenario is basically resolved. So if we look at the perception signaling design, I don't know if I can, yeah. Okay, perfect. If we look at the perception signaling design, then you can see that basically only two elements changed, the red ones here. So this design has as a basis that we don't communicate the intention of the automated vehicle, but actually represent something like eye contact or similar things to transmit the perception of what the automated vehicle actually sees to the traffic participant outside of the vehicle, in this case a pedestrian, and to the onboard driver. And then almost self-explanatory, the next design is the combined version of both. So we actually transmit the perception of the automated vehicle, and then the decision, the intention the automated vehicle took to actually give right of way in that case. So that was the interaction design on a very abstract level. So we're not talking about how actually an external internet HMI looked. And yeah, that's something that we have to do now. And I will hand over to Mark to actually describe the process on how we selected the appropriate display technology to transmit these messages. Mark, we can't hear you.
Now it's better?
Yes.
Okay, so what you see here is just an extract from a criteria catalog we had at the beginning or in the early stage of the project regarding yeah, the choice of possible HMI technologies. And you see something like vehicle integrability. This was an important point, and you see in two cases here the word visibility. What I have to mention here is that we decided in a very early stage that the visual channel is the channel of choice to transfer the messages we want to transfer in different situations. That's not only because Hella is one of the partners and want to sell lighting products. So you can be sure we have also honks and horns and any kind of noise engines we can sell. But we have some specific reasons why light is the right medium to transfer messages from automated vehicle to human road users. And it's easy to explain. I think light signals are well known. They are internationally established for manually driven vehicles today to transfer messages, especially regarding next driving maneuvers and so on. And I think light has one very important advantage. So you can see the also in let's say very complex situations with a lot of traffic participants, a lot of vehicles, you can see the sender of a signal. So you can identify the sender of the signal because of the light emitting surface on the car body. This is one very, very important point, very important fact and argument we used for our choices. And then we have to check, okay, which kind of technologies could be feasible to transfer the messages to solve our main use cases and use cases beyond this. And yeah, you can see an extract of the list we had, and Of course, sound also plays a role for us, especially in deadlock situations. To be honest, we didn't investigate them in detail, I think, but you will hear a lot of it regarding our studies we did in the work package 6 presentations in a few minutes. What we did is we have chosen 2 external HMI technologies in this project. On the one hand, a light band all around the vehicle. Which covers a lot of use cases and which is visible from all sides of the vehicle. This is one main different to the other technologies we have chosen, the so-called directed signal lamp. This was a special research work and also in a PhD work we had here at Hella, with the idea that we can send light signals to only one specific traffic participant. That's the idea behind, and that's I think interesting technical approach to realize a perception-based interaction strategy, just to send signals to traffic participant to whom this message I have detected you, in this case, refers. To go a little bit in detail regarding this 360-degree light band, we have chosen so one important thing is that we had a solution that fits to the car body of the demonstrator vehicle. So we had it was one of the main goals that we have a fully integrated solution, and yeah, we reached this goal. And on the other hand, we deal with a lot of technical questions, how this light band should look like and what should be feasible. And one important question during the last years, not only in this project, also in other projects, consortia, Fora, and so on, was a question about the let's say perfect light color, the color of choice. And yeah, from month to month, from year to year, we saw that yeah, something between blue and green, like I always say, is a color of choice. So sometimes you read the word cyan or blue-green or turquoise as yeah, similar terms for the same color. It's a if you know this CIE color shoe, you can see here on the right side. It is let's say a small area, something between 490 and 500 nanometers. We have to reach, yeah, to be out of the green and blue restricted area. These areas are already restricted for vehicle and traffic lighting. So it's an idea to get an saturated color in between these two. Between these two colors, and that's also one thing we have reached in this project, or we have implemented in this project. Yeah, one challenge, especially for this light band application, was, like already mentioned, to fit into a vehicle's car body. We didn't build up let's say an own research platform. So we took in this case, this is an example, one of the vehicles was a BMW i3S serial vehicle with a space frame structure. So we have on the one hand the space frame as the bones of the vehicle, let's say it like this, and we have the body parts on the outside as something like the skin. And it was a big challenge to implement this technology here, because just if you have a look at this center, let's say cut, you can see here, it is we have around about 10 millimeters between the light source and the reflector, and 10 millimeters between reflector and cover lens. So it's quite a small system. And we have in some more than 700 LEDs around the vehicle. All of them are switchable for themselves, so we have the chance to realize animation, to illuminate segments, but we have a very homogeneous appearance if all LEDs are switched on. This was also one of the technical goals we wanted to reach, and we reached in this project. The other HMI component, I think a little exotic one, and yeah, one of the main difference I think we have to other project is this so-called directed signal lamp idea we have implemented in the project. It's yeah, let's say something like a projector with an special liquid crystal display as an imaging device inside, light sources and reflectors for back illumination of this display device, and a multi-lens system to image this display. The challenge is that we have on the one hand, yeah, 320 channels. We want to realize in a range, in a horizontal range of around about 70 degrees, to send light signals and coded messages like this to only one specific traffic participant. And in one demonstrator vehicle, we also integrated one very first prototype of this directed signal lamp idea behind the windshield of the vehicle. Yeah, this is just a small short animation to get an impression. This is a top view how this signal lamp appears, or how it looks like, how it works. I already mentioned this 320 channels in 70 degrees, and it's also the idea that it's possible to address several addresses. Yeah, this is a short video. Our PhD student, Jan Wilroth. Jan, I think you can hear us. Warm welcome. Made with this smartphone. It's just a 3-second video in an endless repetition, but you see this very first desktop sample we built up here at Hella on the desk, and yeah, one of these 320 channels is open now, and the back illumination is on, and you see when you make a step left, you see a light signal. You make a step right, you don't see a light signal. That's a more or less simple idea behind, but it's a technical challenge to solve this issue. You can be sure. Okay. Then for the onboard users, of course, there were also some investigations. You will hear more about that also in these evaluation presentations later on. But I just want to give you a short hint that we didn't forget the onboard user, and we also had two so-called IHMI, so internal HMI solutions built up for this project. One is a so-called automation display, which is able to send messages or to mirror messages which are sent to the other road users, also to the let's say interested onboard user in special cases. And on the other hand, this is a mock-up, a laboratory mock-up from the DLR with a so-called 360 degree light band for the internal use, where it's also possible to illuminate this light band in different colors, different segments, to give the onboard user the hint, for example, if an object was detected and in which direction, and so on and so on. Okay, then I want to hand over once more to my colleague Florian, who tells you something about, or give you an overview about this signal design.
Okay, thank you. And so before I was telling you a little bit about the more abstract interaction design we developed. Now Mark told us how we selected the appropriate technology to actually transmit these messages. So the step that's still missing is how actually the signals look on the HMI. So basically, once again, we have a look at these flow charts here. We developed different signal variants, for instance, for the message that the AV gives way. For instance, we developed one example would be we have the light band switched on, and once the AV wants to communicate the message that it gives way to another traffic participant, the light band slowly disappears from the front to the back. Or we also developed a variant that the light band slowly turns off, or a further variant where the light band pulses slowly. And throughout the project, I don't want to go into detail into the evaluation because we will hear later a talk by Yimun. We ran studies to actually design in an iterative way and also rule out a few signals by these user studies. So in the end, I told you before we had these three design strategies. In the end, we came up with one design per interaction strategy. So we still had one design for the intention-based, one for the perception-based, and one for the combined. I will show you a quick overview over this in a second. And what we tried to do at first was to basically come up with one single design for interaction, but we found that there was so much potential also in all three interaction strategies that we basically decided to only prioritize and come up with one main design that was included in all the evaluation studies that worked with EHMI, and then we had two secondary designs, the perception-based one and the combined one. And so basically, just to mention the flowcharts again, we are also we're able to then use the flowcharts again to actually describe the concrete signals here. We also have a signal catalog where all these signals in detail, such as their frequencies and things like these, are mentioned. So if there's any more information needed, then also please refer to our deliverable 4.2, where there's a lot more information on that. So I want to go quickly into the designs. So at first we see the intention signaling design. So basically we have the vehicle standing still, and then it starts moving or will start moving. So we see rapid flashing on the light band. I really hope the video transmits to you well. So once the vehicle decides that it gives way, we see a very slow pulsing. Then the vehicle actually decelerates, and we see that the pedestrian in this case can pass. Yes, now he passes. Okay. So if we look at the perception signaling design, the final design that was implemented, we actually have a part of the light band which transmits the signal that the AV has detected you, or in this case, the pedestrian. So basically, as we have the 360-degree light band, the signal can go all around the vehicle and can point towards any addressed traffic participant that we want to highlight, basically, and want to show that he has been detected. So we will see that hopefully in a second with a pedestrian walking by. Okay, so if we look at the combined design, we don't have an animation video of the actual combined design. There actually we combined the intention signaling design that you've just seen in a second with the signal lamp, the direct signal lamp that Mark has described before. So I just want to go into the message that the AV has detected you on the directed signal lamp. So basically, if you have been detected, then you will be able to see the signal in the windscreen that you can see now. And if another pedestrian should be addressed because only he was detected and you weren't, for instance, and then you will just see not see the signal, but the other pedestrian will. All right, and then I think we're ready to implement everything into our demonstrator vehicle, and I hand back to Mark.
Okay, yeah, thank you, Florian. Just the last 3 slides, we should give a short overview and fluent transition to the next presentation regarding integration of the overall system, here with a focus on the HMI components. So this is just a collection of pictures we made during the last 3 years. So from a first idea, from a sketch, and how anything can look like, and which messages can be transferred by which technology and so on. Then we had some workshops, how this EHMI components can be mounted on the vehicle and what's necessary to realize a fully integration. Of course, CAD data, so mechanical design was one main point to get a technical solution for sure. Yeah, then we built up on the one hand our first desktop sample to get an impression how these technologies work, and on the other hand we have virtual reality implementation to make first investigations with VR glasses or whatever. And then all results were put together to build up both components, both external HMI components, lightband and directed signal lamp, and then the integration work here in this case in the tool shop of or the garage of BMW could start it. And we had also a second vehicle, so colleague Fabio Tango will tell you more about this in the next presentation, but just to give you an overview that we have also external HMI, let's say an reduced external HMI component in this CRF vehicle, which is able to have also the communication between this CCPU and the eHMI in this demonstrator vehicle, which is able to run fully automated. And last but not least, this is just a video from a Wizard of Oz study in Munich, so that you get an impression how this vehicle looks like and how one pedestrian reacts to it. And any additional informations you will get regarding these vehicles during the next two presentations. So last slide, Florian and me, I think we will say thank you very much for your attention, and we have 4 takeaways for you. That we have implemented 2 interaction strategies, and that we have 2 eHMI approaches fully integrated into the demonstrator vehicles, and also the 2 internal HMI approaches, like already mentioned, and you will see them from time to time during the next 2 presentations. And I hope you can remember what Florian and me explained during the last 20-25 minutes. So thank you very much.
Thank you.
Thank you, Mark. Thank you, Florian. We are perfectly in time and have some time for questions right now. Thanks a lot for your presentation on the eHMI and HMI developments in the project. Natasha, do we already have some questions from the audience?
We do have quite a few questions.
Okay,
we did have a question for Tom, but I'll wait and see how it goes, and we'll maybe come back to that. Good couple of questions around visibility. So there is one around how blind road users might perceive the light altogether, and then also generally also during bright daylight. I'm sure you're not surprised to hear these questions. So whoever wants to answer that.
Yeah, so okay, blind people, so visual impaired people, of course, they have a problem to perceive light. They cannot see light. Yeah, this is a simple answer, but they have, I think, special problems in infrastructure today as well. So then most people ask the question if it's necessary in the special situations to send an additional sound signal, like traffic lights, for example, do today. We decided not to send this additional signal because we have to send it every time, and then we have additional noise pollution coming from mobiles, also from vehicles, which are not part of the infrastructure. So from my point of view, we can discuss this topic, visual impaired people, this is a special case, of course, but we didn't have a special solution for visual impaired people in the interACT project. And the second one was, I think, what about sunny days and visibility on sunny days? Yes, of course. We can cover also these situations, daytime and nighttime situations, and this is, of course, one of our daily tasks we have here at Hella, that any kind of lighting devices are visible also under, let's say, adverse conditions, and sunny days are adverse for lighting manufacturers.
We learn a new term.
Okay.
Okay, thanks, Mark. So
All right.
now we
Yes.
have a question around two pedestrians. So if two pedestrians are detected, the directed signal cannot indicate intention to both of them. Is that right? And how do you tackle this challenge?
So maybe if I may answer the question, we can show the detection actually to, we might show that to two pedestrians, and we tackle that. That's why we actually chose the combined approach for using the signal lamp, because we can then still communicate the intention that the AV will give way. Yeah, we assume always a, let's say, fail-safe behavior. So if both pedestrians have been detected and you actually see this message that you have been detected, that obviously the AV will not stop only for the other pedestrian, but if you're basically closer to the AV, that the AV will stop for you.
Okay.
Okay.
Quite a few questions coming in, so I'm going to race through them, hopefully. Perception-based EHMI. How would a pedestrian who has not been detected by the AV know that they have been detected? Do they not know that there's lots of not know that there would be a signal if they have been detected by the vehicle? Does that make sense? So maybe just answer the first question is, how would a pedestrian who has not been detected by the AV know whether or not this has been detected?
So if they would not have been detected, they would just not see a signal. So we would, just assume that the legacy behavior today would work in that case, so that people would just not step on the street. And maybe, I mean, we'll cover a bit of that later on, also in the evaluation. So maybe that will answer the questions how people actually react. We would assume that if you are used to getting a signal, basically once you have been detected, that the risk might even decrease, that you actually would step on the street if you have not been detected because you're lacking that signal.
I think this is about the learning effect, and as you said, we will have some more in the evaluation studies that Yimon Li is presenting later. Okay, Natasha, sorry.
Yeah, no worries. So there's some sort of quite technical ones. I'm going to miss a few just to allow for a variety. So did the EHMI lighting require compliance validation with road traffic vehicle standard laws for use on the public road?
So I hope that I understood it right. Today, we have no kind of regulation for vehicles like this and for the lighting devices like this. For example, mounting position of these devices, colors, messages, and so on. So of course, if we want to make real world studies, for example, with vehicles like this, we need a special advice, a special rule to use this. So there are some recommendations regarding how external HMI lighting devices can look like in the future at SAE and ECEs. So not only in Europe, also in the US. But these are recommendations, no regulations at all. So this is something for the future. And today we have to deal with the regulations we have for manually driven, plus some, let's say, additional rules that we are allowed to use these vehicles on public roads. This is something BMW can talk about, because it was, I think, a big thing to get this vehicle on the road. Am I right, Florian?
Yeah, definitely. But let's just say we have permission now to actually do user testing on public roads. So it is doable with the solution that we implemented, even if that's obviously just a prototypical implementation for now.
I think that was more the question, maybe around the testing, whether you had permission to use it on
public.
public.
We do. Yeah.
Okay, so a couple of questions around other road users apart from pedestrians. So do you have any comments about whether the EHMI can also be used for cyclists and drivers, other drivers?
Yes, especially during the research work, which we had here at Hella, also cyclists. This wasn't a main use case in interACT, to be honest, but we had also a look at this. And what I have mentioned, for example, as I explained, this 360-degree light band solution. We had a look over the the main use cases we used in interACT, and that's the reason why we made the choice. Independent from the main signal design and independent from the main use cases, that we can cover more, that we can also send signals backwards and to the side and so on and so on. So yes, we have these use cases in mind, and we know that especially cyclists and yeah, the safety of cyclists and also the traffic flow. Yeah, we have also this decision when a vehicle or an automated vehicle or manually driven vehicle wants to turn right, and the cyclists want to go straight ahead. This is a situation everybody in Europe who has ever sit on a cycle knows. This is, for example, something we have in mind here.
Okay, thanks, Mark. There is a technical question for you, Mark, around lighting visibility. So I'm sure you'll be happy to hear that. How could you manage the choice of the LED bar color on vehicles with very bright colors that do not contrast with the LED bar? So a cyan vehicle, for example, and a cyan light.
Mm-hmm. So this won't be a problem.
Okay, so you
so
can find
this would, yeah, this you can imagine if you have a red car, there is no problem with the braking light, for example, or do you know it, or a yellow car with a turn indicator, or a white car with the headlamps. So this is complete different. The one is just reflects the light of the sun, yeah, or a specific spectrum of the sun. That's the reason why it has the color, this vehicle. And the other one is an active element which emits specific color, a specific wavelength, and specific let's say high luminous flux, that you have a contrast to the, let's say, to the background, to the environment. So you can be sure it works also for a cyan car.
Okay, great. So I'm going to jump back to a question for Tom. Hopefully Tom can either turn his microphone on or his video. So this was about, would you consider connected vehicles that are not automated to be in the context of future CCAM as well? So a distinction between connectivity and automation.
Yes, so Natasha, I typed the answer in the box. I could not read it back, so I'm not sure what I answered there, but I'm pretty sure that I said that we really consider the combination of it. I mean, we think there is a quite considerable synergy in having automation and connectivity together, especially for contextual awareness. But however, that is not to say that we don't see that there is some added value in having just a connected or just an automated vehicle.
Yep.
So the focus is on both.
Answered the same thing again. This box I don't think is available to the audience. It's just for us as panelists and organizers. So that's why I wanted to make sure that everyone who's listening in could hear. So we've got a couple of minutes, but in the interest of keeping on time, I'm happy to move on. Anna, I don't think there's any new questions coming in.
Okay, thank you. So if there are any more questions to Florian and Mark, feel free to add them in the box. As said in the beginning, we will try to answer all your questions and upload the document on the website on the special section of the final event. Thanks again, Mark and Florian. We are now moving on and we'll hear a talk from Fabio Tango on the demonstrator vehicles. So Fabio, it would be nice to get prepared. You're there, all right. Fabio has his background in physics and computer science and works at CRF in Italy, mainly on driver modeling and state classification, human automation interaction, data fusion techniques, and sharing control strategies. Fabio was responsible for the integration and technical testing of the interACT demonstrator vehicles. It's really a pity that we can't show the vehicles in Munich, because a live demo is always better than just having videos. But I'm sure that Fabio will do his best to explain you and let you understand what we did in the project for setting up the demonstrator vehicles. Thank you, Fabio. So the floor is yours.
Thanks, Anna. Yes, I try to do my best for for that. The presentation is about the integration and technical testing for the interACT demonstrator vehicle. And here there is a list of topics I would like to show during my presentation. And this is the first one, a slide that you have seen already other times in this afternoon, just to focus on the two demonstrators that I want to illustrate. And of course, there is a connection of the two demonstrators with all the enablers, all the objectives we develop in the interACT project. So first of all, the context. When we talk about interaction of autonomous vehicle with other traffic participants, in the traditional ways, two ways, human-to-human cooperation, but when we introduce also autonomous vehicle, it becomes a three-way cooperation. So we have to take into account these aspects, and the interACT project developed specific solutions for that we have integrated in the two demonstrator cars, one from BMW and the other one from CRF. Just an overview. The activity I want to illustrate now has been performed inside the work package 5 of interACT. The main goals were the implementation integration of the system components, including enablers and including all the modules, the integration testing of these components and the technical evaluation of the whole system, and then the preparation of these two demonstrators, which focus on different scenarios and different use cases. And now we see which are the characteristics of these demonstrators, and also which are the differences. So the features of the demonstrators. We can say that these two demonstrators have a different focus. So CRF demonstrator, CRF car, focuses mainly on the integration of CCPU, the Cooperation and Communication Platform Unit we heard yesterday, and the perception platform. While the BMW car focuses more on the integration of the external HMI. So we can say that from the CCPU point of view, we have a full integration with all the functionalities of the CCPU inside the CRF car, while in the BMW car, we have only a partial integration, only the parts needed for the functionality of the external HMI. Sensors, we integrated all the sensors of the perception platform inside the CRF car, and no additional sensor from the BMW car. Then from external HMI, we have only a basic integration in the CRF car, while we have a full integration with all the functionalities on the BMW car. And we have just heard the presentation about external HMI. Also the use case are different. The CRF car focus on parking lot, while the BMW car focus on urban intersection. This means that also the evaluation is quite different. For example, the evaluation of CRF is on a private test track of FCA, and the evaluation of BMW is based on Wizard of Odds technique in real traffic. And finally, I indicate also the two responsible evaluation partners. For BMW is University of Munich, for CRF is University of Leeds. Now let's go into details for these two vehicles. Starting from the BMW one. The BMW vehicle is, as you already seen, BMW i3 series car, focusing on the interaction between the vehicle and the other traffic participants in a urban scenario. The vehicle is equipped with a full integration of external HMI, and BMW received a special permission for the testing in real world. Now let's go into details for the for the main components in the BMW demonstrator. You can see here the figure shows a scheme of the components in the BMW demonstrator with the link with all these modules and subsystems. We have basically two components for the external HMI, one for the intention and perception based interaction and one for the perception based interaction. The HMI components are controlled by the control panel, which is a tablet, which is a tablet. We sending the command, the input signals to the HMI control unit, which then forward the specific commands to the appropriate components of HMI, one or two. The signals from the control panel to the ECU is provided by WLAN communication. After that, we have a DGPS system, and this is used to monitor specific vehicle data like position and velocity. And in addition, we have two cameras to monitor the surrounding during the evaluation study or during the technical testing. All this information, together with the information from the control unit of the HMI, are sent to the PC to log all the data. Of course, for the evaluation, this is mainly used for the evaluation studies, but also for the technical testing. And now the integration process of all the components. Here we have different process steps. First, you can see the integration of the GPS inside the vehicle. Then we have the preparation of the series car for the HMI integration. BMW did several integration workshop together with Ella partner in order to prepare everything, to prepare also the EHMI integration, the modifications to the car, the installation of all the components. And here you can see the different phases of this process. And after the testing of these single components, the integration is started and proceed. Which is the result? Here you can see the final demonstrators, the external part of the final demonstrators. You have the front view, the 360-degree light band and signal map, and the frontal view. And then we have also the side view and the rear view, like the final demonstrators of BMW appears. This is the same, but from the internal part, and you can see the passenger compartment with the EHMI control panel, the front camera I mentioned before. The DGPS is located under the back seat, and you can see also the seat cover for the human driver when BMW applied the Wizard of Oz technique for the evaluation. We heard more details about this during the Work Package 6 presentation. Which is the testing process now? Basically, the testing process of the BMW demonstrators is divided in two sections: the component verification and the system verification. For the component verification, we have the test and the validation of the single component before starting the integration. If everything is fine, if this validation is successful, then we can integrate the component inside the vehicle, inside the car. After that, there is the second phase, the system verification, in which we test and validate the entire system, including all components, before the final integration, before the vehicle is ready. This is done, is the second part of the diagram block, and it's done in two sub-phases. The first one is done directly in the BMW body shop, so under controlled environmental conditions, in lab conditions. And when this subphase is positive, is done, the test of the entire system has been repeated outside under real environment conditions on the specific test site. So this was the process for the BMW car. And now we move to the description of the CRF vehicle. The basis for the CRF car is a Jeep Renegade series car. The CRF demonstrators focus on the interaction between the vehicle and the other traffic participants, but now in parking scenarios. The vehicle is equipped with different components, the perception platform, the CCPU, Cooperation Communication Platform Unit, and a basic implementation of the external HMI. These demonstrators has been tested in a private FCA test track. You can see here the picture in which I highlighted the two different areas, one for the test with pedestrian, the other one from the test with vehicles. Test with pedestrian regard particularly the evaluation phase. So we will hear more details in the next presentation about picture 6, but now here I will focus on the test with other vehicles. The main components of the CRF demonstrator, this is a sketch of the architecture we implemented on the vehicle. This architecture, there are some components implemented on the PC and other in the ECU. The perception platform, a part of the modules of the CCPU, like for example, situation match, interaction planning, and so on, are implemented on a PC based, while the trajectory planning and the control motion for the vehicle are directly implemented on a DSpace Micro Autobox 2, because of we need to be very fast, we need to be quite real time. The output is a lateral control reference and the longitudinal control reference, then given to the actuators of the vehicle. I remind you that the CRF vehicle is capable to move autonomously in a given situation. The integration process of all components is shown here. As I mentioned, you can see the external part of the vehicle. Particularly, I show you here the perception platform. You can see there are 6 laser scanner sensors, 3 in the front and 3 in the rear part of the vehicle to cover all 360 degrees around the vehicle. Then we have the external camera and the antenna for the GPS present also on CRF vehicle. And I also put a figure for the external HMI solution. And in the last figure, you can see an overview of the CRF demonstrator like it is at the end of this process. For the internal integrations, for the internal part integration, you can see the trunk of the vehicle in which there is the ECU for the LiDAR sensor controls and the PC for the CCPU. Then I can show you also the internal display, and this display is used both for data monitoring, so for backup or whatever, and also for the onboard internal HMI. Now the testing process for this car. As I mentioned before, we have basically the parking area, in which the idea behind is that the vehicle can move autonomously in a parking area to search, to find a parking slot, and during this movement, the vehicle can interact with other traffic participants, bicycle, pedestrians, other vehicles, and whatever. The interaction with pedestrian, as I mentioned, is for the next presentation. Now here we focus on the interaction with the other vehicle. In particular, these tests are done in the FCA test track I showed at the beginning before, and basically we have 2 scenarios. The first scenario, the CRF demo is going straight on and interact with another vehicle turning on the left, and the second scenario is vice versa. the CRF demonstrators want to turn on the left, and in doing this maneuver, interact with another vehicle traveling, moving straight on. Here, there is the first results for the scenario number 1. So interact vehicle straight on. As you can see here, the vehicle receives the strategies from the CPU. In this particular context, the request to stop within a certain distance. The strategies is provided by constraints in terms of distance and acceleration, and you can see the vehicle is perfectly able to follow these constraints, and the trajectory of the vehicle is inside the left and right borders of the trajectory of the lane. The constraints in terms of distance was, for example, here to stop 3 meters before the meeting point with the vehicle. Even more interesting is the second scenario, in which the interact vehicle turns on the left and the other vehicle is traveling straight on. In this case, again, the strategies provided by the CPU is to stop, giving way to the other vehicle, and then start again to complete the maneuver. As you can see from the plot, the vehicle is able to stop within the terms of the constraints provided by the CPU, and after the other obstacle, the other vehicle is passed, the vehicle can start again to complete the maneuver. Also in this case, the trajectory of the vehicle is perfectly inside the left and right borders. So now, conclusions that we want to provide. First of all, a summary. To sum up, the main results of these integration activities were two main ones. Interact demonstrators ready for the evaluation, next presentation, and interact solutions are evaluated, integrated, and demonstrated. As Anna said at the beginning, unfortunately, we couldn't provide you a live demo of the vehicles originally planned in the final event, the physical final event in April. Which are the lessons learned? What some key points that we want or we have to take into account for future activities? As you say, and as you've seen and as you heard, the integration work has been quite hard work. It requested several workshops, both for BMW, but also for CRF, because of course it's a huge activity. So in this perspective, for sure, we need to take into account of some points, high precision and digital maps and positioning. And this is true for trajectory planning in particular. You, for example, if you think about a classical moving of the vehicle in a parking area, in a parking lot, maybe you are moving, you are traveling to search a parking space, and you meet, for example, other vehicle in the opposite direction in a very narrow road. So it's clear that you need to be very accurate in your trajectory planning. Another need is a 360-degree surrounding view to detect, or from a sensorial point of view, to detect dynamic and static obstacles. And this is important, of course, to recognize pedestrians, to recognize other obstacles, but also, for example, yesterday we talked about pedestrian intention recognition. This is crucial also to avoid unnecessary braking maneuvers, which can be very discomfortable for the occupants of the vehicle, or anyway can create problems to other vehicles following behind. Finally, should be a careful design of the vehicles to take into account the integration of both the sensorial system. You have seen in the CRF vehicle, there are a lot of sensors, and eHMI, external HMI components. And you have also heard from the previous presentation all the work done for the integration of the external HMI. More details are available, in particular in two deliverables of Work Package 5. These are two main deliverables in Work Package 5. One is the deliverable 5.2 and the other one, the deliverable 5.3. Okay, thanks for your attention.
Thank you, Fabio. This was really good to hear how the development for the demonstrator vehicles worked. Thanks for that. So Natasha, are there already any questions to Fabio in the chat?
Yep, we've got one around the sensor configuration. So can you say a little bit about the laser scanners, camera, etc.? How was this decided? Was it based on internal knowledge, or did you have an external advisor on that?
Okay, of course, if Johannes is present here, can add any comments and any details if I say something wrong. No, the decision was an internal decision. At the beginning, it was foreseen to have much more sensors, not only the 6 LiDAR, but also radar and cameras. At the end, we decided to focus only on the 6 laser scanners because able to cover all the external aspects. The camera is used basically for the lane recognition, and the GPS is used with the digital maps is used for the positioning of the vehicle. So it was an internal decision, mainly done by Bosch, which is the provider of the perception platform.
Are there any further comments that you would like to add, Johannes, on this question?
Yes, only one small comment, and that we also use the cameras for the head orientation and also the waving gesture recognition.
Okay, that we learned yesterday, right?
Yes.
Okay. Okay, any other questions from the audience?
Not at the moment. Not sure whether there's any more coming in or not, but no more questions. I hope that's answered the question that the panelist has asked about laser configuration.
Sorry,
Okay,
Natasha, can you repeat?
I was just wondering
There is
whether
a question for me.
No, I was just wondering whether the person who's asked the question has had their question answered. They're not replying, so I assume the answer is yes. So,
all right. And we promise to have some video snippets in our final interACT video of the demonstrators as well, because it's really hard to let you experience how the final design and the demonstrators looked like. But we hope with the video material that we will upload, it's even better to understand what we did there. Okay, if there are no further questions so far, for Fabio, I would like to hand over to our last interACT presentation for today. This is given by Yimon Lee from the University of Leeds. She is a research fellow. Hi, Yimon. And will show you an overview on the evaluation results from the project work. She was leading the work package 6 on evaluation methodology and conducting the test. So thanks, Yimon. We can see your slides and your video. The floor is yours.
Hello. So we come to the part which is talking about the testing, the interACT solutions, methodologies and results for evaluation and impact assessment. So as you know by now, we come to the 5th objective of the talk, which is focusing on the methodology for assessing the quality of interaction. And as you can imagine, in the future, the automated vehicles, in order for it to be interacting well in a mixed traffic environments, the automated vehicles will have to interact with the onboard users, but at the same time, it also have to be interacting with other traffic participants. And what we will be focusing on today is to talk about interACT solutions. So briefly tell you what other solutions is, as well as what kind of methods we have been using for testing, as well as the results that were found for evaluation and impact assessment. So going straight to the interACT solutions, which you have probably been hearing about a lot by now, the first one we're going to talk about today is the safety layer, which is used to eliminate or reduce the severity of collisions and only intervene if necessary. And I will talk about that a little more later. And we also have the solutions for the onboard users, which is the internal HMI, iHMI, which will tell you what are the informations in terms of what the automated vehicles have detected outside the vehicle. And we also have external HMI, which is the information which is provided by the vehicle externally to the other participants or other road users. So I'm also going to go straight and talk about methodologies and provide you an overview of what kind of facilities we have within the interACT team itself. As you can see, we have some pedestrian simulators, we have some driving simulators, and we have also some, the demonstrator that we've previously talked about, as well as the ICCS vehicle. So we do have some simulated facilities, as well as some demonstrators that we test in real world and test tracks. So an iterative process of how we decide on what studies to conduct, what are we going to measure, what do we like to find out. We take into account of literature review, as well as the use cases of interACT, which is presented by Mark Wilbring yesterday, as well as the traffic participants that we are mainly focusing on in interACT, which is the drivers, other drivers, as well as pedestrians, and the interACT solutions, which are the 3 interACT solutions that I've talked about, and coming up with research questions by using different methodologies. We have conducted for about 30 studies by using different evaluations criteria as well. So when it comes to method, you can see that there's 3 big words there, which is the simulator, test tracks, and real world. And each of them really have their own benefits. There's some pros and cons for each of these methodologies. The first one is we're going to talk about a simulator. So simulator is controllable, so it is also easier for us to investigate any cause and effect. So if you observe a behavioral changes in the simulator, you would know that it is because of the manipulation or the independent variables that you have been manipulating in the simulator. It is cost and effective, which means that we'll also be able to evaluate or investigate different scenarios, different scenes very quickly, which you can do in the virtual world. And it is also repeatable, and it is safe, which is very important, especially when we are trying to evaluate a fairly new technology. Providing a safe environment for testing is important, because we don't know how people will react to our solution, and that's what we're trying to find out. So providing a safe environment for testing is very important, and of course it's also reliable. And going to the other side of the spectrum, we have the real world studies, which obviously real worlds have a very high ecological validity and a high realism, because that's what's literally happened in the current situations or the real world, which means that's not something that we might be able to get in the simulator. So for example, in the simulator, we do a lot of one-to-one testings, very simple situations that we're trying to investigate, which often that the real world is very complex, lots of interactions, lots of different things going on, which also makes real world not being able, not a very good way in order for us to try and investigate the cause and effects apart from association. So you would be able to say that when A happens, then we observe a lot of B happens as well, but you don't really know whether it's because of that is what you're observing. And as you can see in the middle, we have the test track, sort of in the middle. It has some controllability, which means you can get your vehicle to behave like how you wanted it to behave like, because you can drive around and say that I'm going to decelerate at this point from that point, but still that kind of control is not as simple or easy as compared to the simulator. But the good thing is that people will also be able to experience the automated vehicles itself in the test track environment, and not only, you know, a virtual environment. So that's the good thing about the test tracks. And we were also able to feed some data from the simulator and also real world to our quantitative models. And what's good about quantitative models is that it has no limit in terms of, you know, the scenarios or how many solutions that you want to model. But the downside is that the model is as valid as what the model can tell you. So that's basically telling you that there's no one perfect solution or one perfect method that will tell you everything. So it pretty much depends on a lot of research questions or what kind of evaluations that we are talking about. So by saying that, we have conducted, using a combinations of different methods, we have conducted 14 pedestrian simulator studies, 4 driving simulator study. We've conducted some test track studies. We've did some observations in the real world, on-site questionnaires, and real world field experiments as well. And so what I'm going to go into next is to tell you some findings or methods that we use for each of these solutions. And the first one I'm going to talk about is the safety layer. So in order for the vehicle to be able to, for the AV to be able to drive very safely in the future, so what the automated vehicles will have to do is to evaluate what is likely to happen in this moment, next moment, so that it will have to be constantly trying to understand the situation as well as plan a fail-safe trajectory just in case if anything happened. So for example, in this particular scenario, we can see that the AV intended motion is to turn left, is to change the lane. So at that moment, the fail-safe trajectory is over there. However, as you can see in the very next moment, what happened is that the vehicle in front decided to change the lane as well. So that ended up to be the most likely trajectory feasible behavior of that vehicle. And therefore, our AV decided, okay, I'm going to move back to this particular lane, and then there will have to be a new fail-safe trajectory to keep evaluating this. And obviously, this is not the only solution. This is not the only scenario that we have tested. So we have created several hundreds of realistic test scenarios in order to demonstrate that, you know, our on-the-fly technique for maneuver and trajectory planning works. And these scenarios were modeled from the real-world data as well as the artificially created data. And we use the threat assessment method, which is trying to understand or evaluate the objective safety of the proposed fail-safe trajectory approach. We also investigate the objective criticality of the scenario by using the time to react measure, as well as subjective criticality of the scenario, so how people felt in this all these situations. And what we found is the key takeaway. So the random simulations of the behaviors of other traffic participants confirmed the proposed safety benefits of fail-safe trajectories in all simulations. So all the automated vehicles remained collision-free and safely come to a standstill. So that's very good news. And these fail-safe maneuvers ensure the availability of safe actions even if the vulnerable road users behave unexpectedly, right? So going straight next to the internal HMI, what we have here is that, so as you remember previously, we have internal HMI, which will be able to provide some information to the onboard driver, what's the vehicle able to detect outside the vehicle. And we've conducted a driving simulator study. And what we've investigated here is that in some conditions, the IHMI information is present and sometimes it's not present. And we also get them to do a secondary task or without a secondary task. And so this is the kind of information that is being shown on the IHMI. So that's how it looks like when there's nothing being detected, or that's how it looks like when the pedestrians is being detected, as well as how it looks like when the vehicles is being detected. So the general impressions from our IHMI study is we have conducted the studies by using 10 participants and only subjective response. And so what we feel is that overall IHMI seems to be useful, satisfactory, understandable, and the vehicle movement was predictable. And why am I saying impressions from the IHMI study is because as you know, that's not too many participants and it is only subjective response. So a lot of evaluations should really focusing on the IHMI solutions as well in the future. Going into the external HMI. So what we've previously learned is that there's different designs of eHMI, which I'm trying to, give you a recall on what we have. So we have the signal, which is called the intended base eHMI. So it is again a 360-degree light band around the vehicle, which is pulsing slowly at 0.4 Hertz, and it is in cyan color, which is telling the external road users that I am giving way. So therefore, it is called the intention-based eHMI. And we also have the perception-based eHMI, which is the directed signal light band in cyan color, which is telling you I detected you. So for example, this part of the light band is partially lit up. So that means that probably the cameraman is standing right in front of here, which means if someone's moved that way, then there will be that side of the eHMI will be partially lit up, as well as any other positions where the pedestrian is located. And so when we talk about trying to investigate the effects of eHMI on road users' behavior and subjective evaluations, so what are the main research focus, or what are the main research questions that we INTERACT have? The first thing is comprehension. So do people actually understand what the signal is telling them? So is there a particular signal which is the best in conveying a particular message? And secondly, visibility of eHMI. So there are some questions around the visibility of eHMI. So that is also what we are trying to evaluate as well. So which signal is more visible than the other, or are they all equally visible? So that's something that we investigate as well. Third is the objective evaluations on how the different eHMI designs affect road users' behavior. Does road users' behavior changes because of the presence of eHMI? That's what we wanted to know. And the subjective evaluations, which is how the different eHMI designs affect road users' perceived safety, usability, and acceptance of the eHMI. Do they like it? Do they not like it? And finally, it's also very important, which is trying to investigate whether there is any potential negative effects. So for example, what happens if eHMI fails? And what about in an ambiguous situation? What kind of impact the eHMI will then create? And so going next to talk about the method that we use in order to evaluate the prototype, so our CRF demonstrator, which we have conducted a test track study by using the CRF vehicle on a pedestrians and AV interaction. So as you can see here that the pedestrians is standing at the edge or at the side of the road, which is having the hands up and trying to react to our stimuli, which is the approaching CRF demonstrator. What we've manipulated is that the distance at which the pedestrians are able to see the approaching vehicle and the eHMI design, so whether it's conditions with no eHMI or whether it is directed light band or whether it is slow pulsing light band. And what we get participants to do is, for example, in one block, we get them to raise their hand if deceleration is perceived, and we get them to raise their hand if eHMI is perceived, and we get them to raise their hand if they decide to cross at that moment, and we get them to rate the confidence levels as well as the safety level at each of these trials. And we also provided some subjective evaluations, for example, the system usability skill, the acceptance skills, learnability, effectiveness, comfort, and safety. And so let me provide you a video of how it looks like. So apologize in advance if the video don't work very well. So as you can see, the pedestrians looking at the other side of the road, and when prompted, the pedestrians will then look at the approaching CRF vehicle and then respond to the vehicle by putting the hands up, depending on what question we were asking at that point. So this is how it looks like when we were testing the CRF test track vehicle. So, whoops, sorry. What we have next is that the BMW test tracks and real-world study. So we conducted 2 separate studies for our BMW demonstrator, which is also trying to investigate the interactions between the pedestrians and AV. And so in the first study, similarly to the last one, we have also manipulated this deceleration onset distance of the vehicle, as well as testing different EHMI conditions. For example, the intended base, perception base, the combined, as well as the no EHMI conditions. And we get pedestrians to press a button if they understand the intention of the vehicle, as well as take a step forward to cross the light barrier to record the crossing decision. And we've also conducted a real-world study for the BMW demonstrator. So if you can see over here, it's that that's the intended path of the driving path of the demonstrator, the BMW demonstrator, which is highlighted in blue. And for pedestrians, we also get them to walk around the pre-designated route. So they were asked to walk around in this route. And as you can see here, that will be one interactions that they will have to encounter each other. And that's when interactions happened, as well as we have another one over here. And what we did is to also manipulate different EHMI conditions, as well as there's 2 different crossing sites. And pedestrians' task was again to walk on the pre-designated route, and they met the AV at 2 stopping points, and we conducted structure interview evaluating the perceived safety as well as acceptance. And next, I'm going to show you a video of how it looks like from the pedestrian's viewpoint. So the pedestrians will have to walk in the route which is designed for them to walk into, and encountered an approaching BMW demonstrator. As you can see, the EHMI partially light up is also following our pedestrian. So that is the directed light band. Yep. Going to the next slide. So what I'm going to do now is to provide you some of the findings. It is some of the findings, not all the findings, and what we know by now. So in a pedestrians AV interaction studies, the first question is visibility of EHMI. Which signal is more visible? Even though they are all perceivable, there are still some signals which is more visible than the others. And what do I mean by more visible is that people are able to see the EHMI at a further distance, or they also rated that the EHMI is more visible than the other ones. And in our CRF test track study, we found that people, the visibility of this, which is the partially light up light band, is more visible than the other one. And next, for example, in our pedestrian simulator studies, we also found that the typical flashing headlights is more visible than our slow pulsing light band. And also in some situations, we also have pedestrians or participants who mentioned that they were not able to see the EHMI. So that's probably under the very bright sunlight, or there are some situations that people will not be able to see, but there are some cases like that, but not all. So this is not to tell you, you know, in terms of whether that is then better than that one or whichever. So by using, and also by using a simulator in order to test the visibility, you will only be able to compare one design to another, which is very limited to the simulator environment, which is then very different from whether people are able to see the EHMI when it's outdoor, which have a totally different environment. And why is visibility important is because if people are not able to perceive the EHMI at the point when it is intended to be perceived, when the information is provided to the other road users, then there will be a delay in terms of, you know, people's responses. Therefore, it is a very important topic about the visibility of eHMI. And next, we're going to focus on answering how the different eHMIs affect road users' behavior. So this is a pedestrian simulator studies in the Hiker at University of Leeds, in which we are trying to investigate the pedestrians' AV interaction. So the pedestrian standing at the side of the road trying to cross between the approaching vehicle. So I can see that it did not go very well. Anyway, so what we found is that the presence of eHMI do reduce the crossing initiation time. So people do cross early because of the presence of eHMI. What about from the driver's perspective when it comes to driver's AV interaction? We conducted this study in a driving simulator. And if you can focus over here, that's the diagrams of the scenarios and the task of the driver. So that orange box is our driver, which is our driver participant, and the arrows is showing the intended pathway of our driver. So in this scenario, the driver's intended pathway is that it has to pull out at the junction, turning right, and in that situation has to pull out at the junctions, turning left, and in that situations, the drivers will have to turn into the side road instead. And what they have to do is to decide whether it's safe to pull out or not in between the approaching vehicles. And as you can see, then they will have to be interacting with the AV. And what we have found is that with the presence of eHMI, it increased drivers' gap acceptance. So as you can see here, when the eHMI is present in addition to the brake, then there is about a 20% increase in terms of drivers' acceptance. So what about the TestRact study? So we also seeing from the driver's AV perspective, we also conducted a TestRact study where we get our driver participants to be driving at the intended path as highlighted in green, and we also have our AV, which is a visit or walk study. It's also intended pathway, as you can see in the orange route. And you can see here in the middle, they will then have to, interact with each other where they encounter each other. And what we found is that with the presence of eHMI, it decreased the duration of interactions. So when they arrive at the little junctions where they have to be both in that situation, the presence of eHMI do decrease the durations where they both stay there. So what about looking from the quantitative modeling perspective, looking at the pedestrians' AV interactions? So we talk a lot about, people cross quicker. What about how do optimize or the exaggerated deceleration and eHMI actually impact the interactions efficiency? So that's very important to know. So as you can see, that's the simulations with the quantitative models of interaction. Let me explain. So what you have here in the x-axis is the initial time to arrival of the vehicle. And on the y-axis, what you have here is the mean time loss reduction in seconds. So this graph is providing you the vehicle time saving with optimized deceleration as well as the eHMI present. And so which means the higher it goes, the better it is, because then they save more time, so the vehicle save more time. And as you can see, the three lines represent different speeds. And there you have a very similar graph, but now it's representing the time that is the pedestrians is saving. And what we have in terms of key takeaways is both the optimized deceleration and the eHMI save time, and up to about 1.5 seconds for the AV, and also up to about 3 seconds for the pedestrians in terms of time saved per average interaction. And with the eHMI, the optimal deceleration is then milder, which means the deceleration of the vehicle do not have to be that much of an exaggeration. and greater time savings in situations with larger safety margins as well. So we also conducted some cross-cultural comparison between the Japanese road users as well as the UK road users, and we found that the UK road users have a smaller safety margin, as well as situations like driver turning situations or pedestrians crossing situation. Then the safety margins of the pedestrians crossing will then be lower. Therefore, the greatest time saving will happen with the larger safety margin. And what about subjective evaluation? So we've been talking about a safe time people cross earlier, and there's shorter interactions, there's higher gap acceptance. Do people actually like it? Do people accept it? So generally, pedestrians felt very safe and comfortable interacting with the AV with an eHMI in our CRF demonstrator vehicle. And eHMIs were generally well received with high ratings of usability, acceptance, learnability from both the pedestrians and the driver's perspective. So that's good to know. What about negative effects? It's something very important. So we want to know what happens if the eHMI fails. So when we talk about eHMI fails, is when the eHMI is on, but now this time the vehicle is actually not yielding for the pedestrian. So what we have done here is simulated studies in, again, the hiker pedestrian lap, and then we investigated the pedestrian's AV interaction. So let me explain what's happening here. And so what we can see here in the gray area is the road, and over here at the side of the road, that's white color, as well as the other side of the road. So these people are at the edge of the road, and these dots represent the location of our pedestrian when the approaching vehicle has arrived at their crossing path. So in other words, so what's happened here is that these pedestrians have not crossed yet, and these pedestrians have crossed, and these pedestrians are on the road when the vehicle is located at the same locations as them. And so these are illustrations of the non-yielding trials only. So before we introduce a failure trial, people have been encountering situations where there is yielding vehicle with functioning eHMI, yielding vehicle without eHMI, trials without yielding, and then after a series of exposure to the functioning eHMI, we introduce a failure trial, and what happened is that it creates about 35% of crashes where people decided to cross the road when they see the eHMI without really evaluating whether the vehicle is decelerating for them or not. And we have a second failure trials, which we introduced at the end of the experiment, which you can see here, a lot of people have learned their lesson, so there's less crashes here, but on average, there's about 30% of collisions that happens if eHMI failed, and if it's intended to tell people that I'm slowing down, but it is not. What about from driver's perspective? What happens in the more ambiguous situation? So again, we conducted a driver AV interaction in a driving simulator study. You are probably very familiar with how to read this diagram. So at the end of the experiment, we provided one single trial, which we also looked at what happened if there is another approaching vehicle at the right-hand side of the road instead. So this is the exact same scenario as that one. Apart from that, we added another vehicle on the right-hand side. So when the eHMI is present, there's 4 out of 22 people who did not look at the other side of the road and causes a crash. And 6 out of 22 did look at the vehicle at the other side of the road and therefore created a near collision as well. We have about 12 out of 22 drivers are fairly safe in this condition. So our general impression up to now is that if eHMI was present, then participants relied on the eHMI to infer intention. However, when the eHMI was absent, then they used vehicle kinematics to infer intention. And going to the summary and conclusion, so going back to the safety layer, so the incorporation of the interACT safety layer proving that the vehicle never causes an accident. So these fail-safe maneuvers ensure the availability of safe actions, even if vulnerable road users behave unexpectedly. So in turn, we do expect that then the proposed safety layers will increase the comfort and trust of the humans in AVs. And our observation studies in conventional traffic situations, which is the current traffic situation, so presented by Andre yesterday, we showed that the explicit communications rarely happened. A lot of interactions are mainly resolved by implicit communications, well, at least at the site that we have chosen to observe. However, so we did observe more explicit communications in some scenarios, for example, the parking scenarios, which probably because there's lower speed in parking scenarios. And we also found some associations of when drivers who use signals are also more likely to take priority than other drivers who do not. So there might be, the effect of the explicit communications. What we saw is then there is an association with what we are likely to also observe in those situations. But our evaluation studies also show that participants are able to use kinematics information as a cue without the need for EHMI. So we have some studies that found no difference in crossing decision. For example, the BMW pedestrian simulator study, there's no difference in crossing decisions in our CRF demonstrated test track study, mixed findings in our BMW real world study. However, EHMI can also induce early crossings and shorten the interactions time, and therefore improve the flow if the visibility and consistency of EHMI are ensured. So visibility, again, is very important. If people can't see it at the point where it is intended to be seen, then there will be a delay in terms of people's reaction, as well as consistency is very important, because we know that if it is not providing the information that what the vehicle is doing, then it might create something that we don't want it to happen. So overall, there is quite a very positive experience was reported subjectively by participants, but we need to be really cognizant of the potential of new types of crashes that we might be introducing, and the consequences of the EHMI failure or either miscommunications can be severe, and therefore, the public guidance around the EHMI capabilities will be required, and definitely more studies required on the potential negative effects of EHMI. So caveat, the conclusions are really based on a very small number of studies, and analysis are still ongoing. There might be new findings that we'll be able to find within interACT ourselves. We are all still learning, and especially in this very early stage of the entire research topic. So more studies should be developed to understand the interactions in more complex scenarios. As you can see, a lot of our studies, regardless of whether it's test tracks or simulator, is a lot to do with one-to-one interactions. So we need to do more complex scenarios, trying to understand them across different situations, scenarios. For example, parking, we talk about parking might have a more explicit communications going on, as well as, for example, deadlock situation, understanding the long-term effects and behavioral adaptation are also very important. So talking about doing more studies, so in terms of methodologies, reflecting back, so what we actually feel is that there's more effects or stronger effects of EHMI being found in simulator than our test track or real world studies. We don't know why. It could be the methodology that we're using, could be the environment, or it could be the speed of our test tracks, or the real world vehicle that we have been testing is different from the simulator, or it can also be due to the visibility of the EHMI in the simulator, which is, is a simulated environment, and therefore it's much more visible than when it is in test tracks or outside the world, in the outside world. So that is all I have, and that's the references. And thank you. That's the end of my presentation.
Thank you, Yimon. That was an excellent overview on all the work we did. You might feel a bit overwhelmed right now. So as Yimon said, we are still doing some analysis. We will still work on publication for conferences. There's a lot out already, so this was your reference list, Jimon, thanks for that. And most of the publications are available on the website. But if you are interested in the topic, I would advise you to follow us further. Even when the project is ended, we will be available or present on conferences for sure this year and next year with the results of the project. Natasha, are there any questions coming from the audience?
Yes, absolutely. Just want to say well done, Yiman. It's really hard in these virtual situations not to clap for everybody, but clap to everybody this afternoon. Some great presentations, and there's a lot to cover. So I'm glad it was you and not me. So yeah, quite a few questions coming through for you. Maybe not all of them will be answered by you, because obviously this was you presenting the team's work. So we'll start, I'll do it in order and we'll see how we get on. We've got about sort of 15 minutes or so. Right, so the first one is about the IHMI. Does it also indicate the relative position of pedestrians or vehicles with respect to the car?
That's a good question. So I need to pass that question to the group who did the IHMI studies.
So whether that is Mark or Fabian, who can understand. So effectively, is it the same as the EHMI in terms of directionality? Does the IHMI identify the direction and position of the pedestrian?
I think it's easiest if Mark Wilbring from DLR is answering this question, because then we do not need to make Fabian a panelist, or is he already?
Yes, he is, but Mark,
okay, Mark
can do that, yeah.
Oh, okay, sorry.
Okay, I think I can do this, yes. So for the evaluation, we just tested this automation display, and this automation display has no information regarding the local position or environmental position of the pedestrian.
Okay, and this is different for the light band, right?
Yes, so if we would have
HMI,
used the light band, then yes, then we have a directional cue regarding the environmental position of the pedestrian, yes.
All right, okay, thanks.
I'm not 100% sure about the answer to this question. So did we test any, did we do any tests with multiple pedestrians? Did anyone do any tests with multiple pedestrians, or we focus more on just one?
I think BMW did a pedestrian simulator studies which involved different pedestrians. So I'm not sure if Florence wants to talk a bit more about the study.
Yeah, we actually did a study where we had, can you hear me? Yeah. Where we had another simulated pedestrian, and we're actually looking, that was still in the development phase of the EHMI. We're looking if there were any differences between the EHMIs regarding, let's say, confusion that might be caused, for instance, as the intention-based EHMI is not differentiating between who is addressed and where the pedestrian is standing. And we did not really find any problems there, let's say. So at least for pedestrians, they just relied on the legacy behavior. It did not just jump on the street just because there was an EHMI signal coming up.
Okay, thanks, Florian. There's a question about the situation with the turn left of the AV and the manual driver. What type of EHMI did you use for that study? Not quite sure which one that is. It mentions a white Toyota, but I don't think we had any white Toyotas.
Oh, that's the ICCS equipped vehicle.
Okay.
So yes, let me go back to the slide. I hope you can still see my slide. So yes, in that situation, the vehicles always turn left. I think that's the only scenarios that we have tested. So I think the question is whether the vehicle turned the other way. Is that the question?
Which type of EHMI did you use for the study with the turn left situation? That's
right. So what we have got here is that a very small, slow pulsing light band, which is the the way that the interACT solutions have designed, so it's the same hertz as well, but it is not the full light band that will be able to fit into that car because it is not our main demonstrator. But ICCS did a very small demo in terms of showing how that slow pulsing light band will also simulate in this vehicle driver's interaction.
Okay, thanks.
Okay, thank you. So there's a question about which side of the road is important, and I think the general answer is no, there is not any difference as long as people know which side of the road to look at, obviously. So all our studies, we made sure that the pedestrians and the road users were resident in that country for a while, so they didn't get confused about which side of the road to look on. There's a question about distracted drivers. I don't think we looked at distracted pedestrians. I don't think we looked at distracted pedestrians in interACT, but we are looking at that actually in Leeds with a current study. Big question to the whole consortium around whether or not we would recommend EHMI for AVs, yes or no. I don't know if anyone wants to jump in and answer that.
I think at this point, before saying whether we recommend or not, we really do need to have more information than we currently have in order to answer that question. So as mentioned in some of the conclusion or summary, that there's a lot of other scenarios or situations that we have not tested just yet. And there's still a lot of investigations that's needed to be done in terms of whether people can see it, what about people are distracted, what about long-term effects, whether there's one scenario is definitely needed as compared to the other scenarios, whether there's a third type of negative effects that we might find. So all this information is really important for us to gather before we can really make a recommendation on whether EHMI is needed or wanted or not. So these are, at the moment, based on the very small amount of studies that we have laid out, the current findings that we have.
Okay, thank you, Human. I think it sort of answers the next question about whether there's anything that you observed in your one-to-one studies which has relevance for future studies in terms of the complex interactions that actually happen in the real world. So is there anything you want to say that will help for looking at real scenarios and real world, not just the one-to-one situation?
Yeah, so we do have plans to, try and expand more than the one-to-one interactions, and we are really supposed to do one final studies in Leeds as well, which is trying to look at, more interactions or a few other agents that road users that we have to be interacting with. But because of the pandemic, then things have to be delayed. But definitely, even if it is not within interACT, it's very important questions to answer as well in the future.
I think the question was more around what would it be, and I guess one thing off the top of my head is that there is definitely behavioral adaptation and learning by pedestrians. So it's all very new and it's all very ill understood, but we are seeing that actually as people understand what's happening, as long as it doesn't contradict itself and it's intuitive, it can be then learnt, and so hopefully that will help with others around to help that. And of course there is some work being done around whether groups are influenced by individuals, and I think that's an important aspect to look into further. Does anyone want to add anything else to that? Okay, I'll run to the next question, which is how did you determine the optimal deceleration for the vehicle interaction study? What do you think may account for the differences between the CRF study and the BMW study? So there's two questions there.
Okay, so the first question is, how do we decide the optimal for the demonstrator vehicle. So first of all, the CRF vehicle, what we have is that the vehicle is definitely traveling at about 12 kilometers per hour. Yeah, so that's around the speed that the vehicle is capable of doing. And therefore, what we have done is to come up with different distances at which the participants turn over, and that's also being counted by the time to arrival that is most likely that people would have the kind of interactions, which also based on some of the previous studies that we have conducted in not involving eHMI, but trying to understand, for example, at 3 different speeds and 8 different time gaps, what are the very likelihood when people will be interacting. So we know that if the vehicle is 8 seconds away, then there's very less likely the interactions will be happening. So we are trying to understand, for example, from the 3 to 5 or 6 seconds, and that would be the decision that we trying to make. I'm not sure if the BMW and TUM team wants to say something about the test track and real world study.
So I can jump in quickly. Basically, for the BMW study, we had light barriers that actually switched on and off occlusion glasses. This way, we actually could set at which position of the vehicle the pedestrian was able to actually see the vehicle. The deceleration, we just figured out some distances at which the car will start to decelerate, and we aimed for a minimal deceleration maneuver, basically meaning that you try to decelerate as constantly as possible until you come to a full stop. So simply because we had some studies beforehand in simulators finding big differences in if you kind of decelerate aggressively at the beginning of the deceleration process or at the end. This had like some influences, and therefore we decided to have like the most comfort possible approach, which means a minimal deceleration trajectory. So this was how we determined our deceleration in these studies. Of course, maybe another deceleration profile would be best, especially when coupled with an eHMI. And for the question, are there differences, or why are there differences between the studies? Probably because of the study design. The BMW was driven at 30 kilometers per hour, while the Fiat was driven with 12. So probably therefore we had seen some differences. And also we opened our shutter glasses at a TTA of approximately 8 seconds, which means we had 10 to 20% pedestrians crossing before the car actually did anything, right? Mm-hmm. So maybe this also influenced like the comparability to the other study.
Thanks, Andre. Okay, the next couple of questions are around the pedestrians. So I can quickly answer one around whether we actually chose high risk, low risk people as pedestrians. We certainly looked at the personalities using a sensation seeking scale to see whether there were high or low risk takers. I don't know whether anyone else in the partners actually chose particular groups. I don't think so, Yiman, is that right?
Yeah, not that I'm aware of.
Okay. And then there's a question around trust and comfort, and certainly we did look at trust and safety, not comfort. Difficult to know what comfort would be relevant for the pedestrians, but again, yes, there are some questionnaires around that. Okay, so there's another question about what would happen if the user would also start to communicate, e.g. by hand gesture. So I guess that's above and beyond what they're allowed to do, and I am assuming that's around the in the real road rather than the simulators, but I don't know, Yiman, if you want to add anything on that.
So this is more about whether the vehicle will then receive an information about the hand gestures from the pedestrians. Mm-hmm. It's not what we look into in Work Package 6, but I'm not sure if we want to talk about the detection side of stuff, the intention recognition part. Did any kind of recognitions in terms of hand gesture, Anna?
Just yeah, this is sorry, yeah. Go ahead.
Yeah, I think the question means what happens if the driver starts waving and the eHMI is showing. I'm quite sure it goes into this direction, which would probably be a quite bad thing, of course. And yeah, but this is nothing that we looked at in interACT.
Yeah, I think this was the main idea of having an IHMI, English and German in this case, IHMI available, so an onboard HMI available also for the driver, so that he feels safe and know that the automated vehicle is in interaction with someone in the surrounding and does not feel the need to step in to interact with the pedestrian on a zebra, for example. So this was covered by the design and some tests done at DLR.
And maybe one additional comment to that, with the external HMI, we started communicating quite early. So probably, at least in the test track study done with our demonstrator, the waving of the driver should not have been completely visible at the moment where the HMI actually switched on. So the contradicting information should not have been present at the same time.
Okay, we're bang on time, and I'm very proud of that.
Excellent.
So let's continue with keeping to time. So I think we haven't got any more questions anyway. So thank you, Yimon, and we hand it back to Anna.
Okay, let me share my screen then. Sorry, my screen looks not as I expected it to look like. So, all right. We are coming to the very last presentation for today. Thanks for staying online for such a long time. I think we have a plenty of results, so I believe it's nearly impossible to understand everything just from the webinar today. But let me try to wrap up the session and present some conclusions. So we talked mainly about the 5 objectives of this project, the interACT project, and we tried to give you some insight on what we did to achieve a safe integration of automated vehicles in mixed traffic environments. As Tom mentioned in his keynote speech, there are further development. It goes into the direction of complex testing and human factors, and HMI and sensing technologies are not the only factors, but of course they are quite important. And I think this is also what we've learned from the project 3 years. This is a long period of time, and we really had a great team in interACT doing all this work. Very engaged people, very interested in the topic, but of course some questions are still open. So what we learned for sure is that we had an understanding for the, sorry, I need to fix my screen, otherwise I can't see my slides. Okay.
So Anna, just while you're doing that, I just want to remind people that we've got some Slidos towards the end, and we've got some nice pictures also from Anna. So do stay on and see those if you can.
Okay, thanks. So now I just kicked out the web stream. All right, so I can see my slides now as well. So what we did are some cross-cultural observations, and I think we gathered a good understanding for human-human interaction, as mentioned by Yimon in her presentation. Of course, we focused on a tiny bit of situations that could happen in real traffic, so presented by Mark yesterday. The human interaction models that we developed are quite promising and of course can be enlarged to other situations as well. We have an improved intention recognition. The algorithms were developed by CCS and Bosch because we believe it's really relevant to have an idea what's going on in the surrounding of the AV if we would like to react to these situations. So this is one improvement that we could make within the project. And of course, there was a completely new development of the cooperation and communication planning unit. And this was fully integrated into the CRF vehicle. It was not an easy task to integrate components, software components coming from the different research departments of the different partners. But I think the colleagues did a great job to come together in Italy and to integrate everything in the CRF vehicle so that this vehicle was able to run automatically and to be evaluated by the studies conducted by leads. Further, we have a newly developed eHMI and HMI elements, and also the first prototypical implementation in the demonstrator vehicles. You have seen videos of the BMW and the CRF vehicle where we did the implementation. And of course, and this was the last presentation, the evaluation results of the project. We did a lot of studies for intermediate and final solution. And I think we all learned a lot about the advantages and also disadvantages of virtual reality studies, simulator study, test track studies, and Wizard of Oz studies that we conducted within the project. You all know when you are writing the proposal for a project, you are asked to say what impact do you expect from the project. So I just put that on the screen as well. With regard to road safety, we have implemented the safety layer in the CCPU that avoids collisions, and higher perceived subjective safety was assessed in the evaluation phase of the project by eHMI, but also by the vehicle movement design. So it's not just about eHMI components, but I think it's a careful balance and good tuning of the vehicle movements and the eHMI that needs to be done in this area. User acceptance and ease of use of automated vehicles. The user needs were considered in the whole design process. We started quite early with the first virtual reality tests to find out which design that Florian and Mark presented would work best, and we selected the design according to the study results. And we have evidence from the evaluation studies that the eHMI could increase the subjective acceptance and satisfaction in interaction with the AV. Validation procedures for automated vehicles. We have, and this is what Yimon also presented today, reviewed a new evaluation methodologies with regards to human factors and HMI questions. And of course, the novel and on-the-fly techniques for maneuver and trajectory planning, mainly coming from the Technical University of Munich, included in the vehicle automation as well. And those allow to further reduce validation costs for automated vehicles. What is important for Europe and the European funding is, of course, the leadership of industry. This will be reported in a separate deliverable, but what we reached within the project is higher TRL levels for several technical developments compared to the start of the project. For example, Mark Howe presented the eHMI component developed by Heller, the newly directed signal lamp. For example, the CCPU was not existing when we started the project. So this as a summary, as a first insight on what impact we think we achieved within our project work. And before you leave, as Natasha said, we would like to ask one Slido or two Slido questions again. And then for the end of the project, a final event, the virtual one, as we can't be together, we have picked up some pictures of 3 years of successful interACT work. So Natasha, are you able to just share your screen with the poll questions for Slido? Once again?
Yes, is my screen, or maybe you can make me presenter, please, and then I can do that. So some people are already responding, so I guess it is open, but you can see it now. So just want to know again what your opinion is about how important external HMI are. So I asked this question at the beginning, but I've added it to see whether how it's influenced the presentations have influenced your opinion. So it'd be interesting to know. So it's very, very even.
It's more or less more or less the same than in the beginning.
Yeah.
What do you think? Yeah.
So we still have around 90 people online. So we'll see. Well, I'll wait a little bit longer before we move on to the next question.
So for those who didn't join us yesterday, you just need to go on the website slido.com and enter the code there. And then you will see the questions on your mobile or PC, whatever you use.
Okay, going to the next question. Please give us your ideas of what you thought of today's presentations. That would be good to know. We will not punish those who get worse for today or yesterday. Everyone gets a prize. Okay, I think
that's really nice.
That's very good, yeah. Right, and then the final Slido question, which is a word cloud. So maybe you can just write a word about what was the most interesting result from today, and it would be nice to see what you thought of it. So just simply type that in, please. So it says voting closed, not quite sure why. I might just have to go back and
you can't
open
type it
that
in.
up. It might be something that I've done, so bear with me 2 minutes, sorry.
Oh,
Right,
okay.
there we go.
Now we can see it.
Well, it's nice to see that there is a relevant word there, EHMI, rather than something completely random.
Oh, yeah. We had a highly concentrated audience this afternoon again. So yesterday it was about modeling, and today EHMI and evaluations. Yeah, okay.
So
people are still typing, so.
Yeah, and while this is live, I just wanted to say, if any of you are on social media, please do give us an idea of what you thought about the last couple of days using the interACT hashtag. If you go onto the interACT website, you can find some of the tweets that have been going on, and just you can use the hashtag to add your opinion, please.
Okay, but I think it stays with EHMI.
Yeah, this can still
and
carry on.
evaluation methods.
You can carry on, Anna.
Okay, thanks. Okay, there was one question about the material. Maybe I forgot to mention that in the beginning. So the material of this event will be uploaded on our website. There will be a special section for interACT related final event material. You will be informed by our dissemination managers from ICCS as soon as the material is uploaded. So the video stream of this webinar, as well as all presentations, additional material, and the interACT final brochure. I guess it will be available early or mid of next week, and you will get this information. So as we can't meet at the moment face to face, and as Tom said, we are all missing the meetings, I would say. Let me take the chance to thank first of all our keynote speaker, Tom Alcombs, who joined us yesterday and today. Thanks, Tom, for being with us. Let me thank all presenters. You stick perfectly in the time. That's excellent. And let me thank all interACT partners for the great teamwork that we had over the past 3 years. And we will end this session at least with some pictures from the interACT project work. That was really a pleasure to work with you. Thank you for listening and following us. As said, there will be more material available and we will be present on conferences as well. So thank you for joining. Natasha, thanks for being my co-moderator and the IT professor of this exercise. We hope you all enjoyed the webinar and the 2 days with you and this virtual final event of the interACT project. Thank you for joining.
Bye-bye. Thank you.
Yeah.
Thank you. Great.
Bye.
Thanks for the great moderation and the great lead in the project.
Thank you.
Bye-bye.
Bye.
Thank you all. Bye-bye.